Good morning, everybody. For the plenary session this morning, we have Harney Wang. Excuse me, Harney Wang. We might have a short presentation about next year's QPL at the end of this session, but I'll let you know in the Q&A if that's going ahead, and in which case hang out on the stream for another 4 or 5 minutes. I think that's all that I need to say this morning. So yeah, I'll introduce Harney. He's talking about Enter a Visual Era, Process Theory Embodied in ZX Calculus.
Okay, can you hear me? Thank you for your introduction, and thanks to the organizers for inviting me. So today I will talk about the ZX calculus. But actually, the first half of the title and the visual error is borrowed from Constantinos' Twitter. So thank you, Constantinos. So I will talk about the quantum mechanics and give introduction to ZX calculus and about components and applications and further developments. So let's start from the basic assumption of natural science. So natural science has a basic assumption, so that exists a kind of objectivity, independent of any consciousness. So the moon is still there when nobody looks. But there is an epistemic issue there. That means we can verify, we can know any existence by our consciousness. So we cannot verify such objectivity. So is there any theory that has more reasonable assumptions? So I would say that the process theory is such a theory which has abstract description of how things happen and based on minimal assumptions. So why is minimal? So first, because we can assume that there must be something happened in the world from some type, let's say A, to another type B. So this type, this can be called as a process, and we denote by a box. And second, we can assume that things won't happen once for all. That means it won't be that all the things happen simultaneously and then nothing happened anymore. So there must be things happened sequentially, so which means first some process G happened and then another process F happened. The first G and then F happened can be seen as a single process from type C to type B. So that means processes admit sequential composition. And third, we can assume that there should be different things happen simultaneously. So rather than just one atomic thing could happen. So two processes, F and G, happen simultaneously. They can be depicted as two boxes they put in parallel. So if we view two types, let's say A and C, as a single type, so we denote it as A tensor C, and then we describe processes F and G, which happen simultaneously as a single process from type A tensor C to type B tensor D. So that means we can have a parallel composition of processes. And also, in the above depiction of F tensor G, this is not a symmetrical way. That means F on the left, but G on the right. But why? So basically, G, if we swap their places, they should be essentially the same. But we need to keep the type match. So we need logically we need the swap processes such that this diagram holds. So with these basic assumptions, it's natural to formalize process theory in the framework of strict symmetrical monadic category. And also if we consider quantum processes, and then we need entanglement structure, which is composed of caps and caps. They satisfy the snake equations. So the entanglement structure plus the SMC, then you got CQM, which is proposed by Samson and Bob in the Leaks paper. And also, we can look at the compact structure in a another way, which is a space-time interpretation. So intuitively, the time should be a form which allows the processes to happen sequentially, and space should be a form which allows processes to happen simultaneously. So a compact structure can be seen as a mechanism which relates the space and time to each other in the sense that sequential composition and parallel composition, they are convertible to each other in this diagrammatically. So for now, we have the CQM, but there are two curious Spider-Men called Bob and Ross. They want to look inside the box of each processes. So basically, they fill in each box of CQM with their favorite green and red spiders, and they got called DS calculus. And in this way, we are doomed to say that DS calculus is a fine-grained version of CQM. And so how do these boxes, these spiders behaves? So basically, they first, how do they build up the process, the spiders in the process box? So they do it in a Lego way. They use spiders as their building blocks. It's the red spider, the green spider, and the red spider. And they compose by connecting their legs or put them in parallel, like what do you play Legos. So these two operations we denote by the circle and the tensor. So what the behavior of the spiders? So basically, for the green spiders, they love each other. So when they meet, they just fuse together. And similarly, the red spider, they love each other. So when they meet, they also fuse in a single one. But so green spiders, they hate red spiders. So when they meet, they fight and then they fall apart. So that's their behavior. And so that's the cartoon style of the spiders. And usually we draw them indicted as this way. So there is a green spider and the red spider, they have N inputs and M outputs. So how to further guide their behaviors? So you can do it by add more loops. So for example, you add the copy loop and the bialgebra loop. But how do we ensure that these loops are really added to white Spider-Man rather than randomly by some monkeys? So in other words, so how do we guarantee that there's no conflict there? So that means you need to use some reliable system to test this system of spiders. So we are very familiar with the matrices. So we use the system of matrices to test the spider system. So that means we interpret the green spider in a sparse matrix is 1 and equal alpha, and all the others are 0. And similarly, you can do another use the matrices for the green spider. And so then once we have this matrix system to interpret the spider diagrams, then we can check so whether there is any conflict in the spider DX system. That is called Soundness. And this soundness can be done by verify each DX loop whether hold in under interpretation in matrices. And it is already proved by Bob and Ross that the X is sound in the original paper. Another problem is, so is the ZX calculus expressive enough? That means, can the spiders represent any matrix of proper size? And in other words, is ZX calculus universal? The answer is yes. It's also answered by Bob and Ross in the original paper. And this property is that is ZX calculus powerful enough? That means if everything derived from matrix operations can also derivable in ZX diagrams. So if yes, then ZX calculus is called complete. So actually, the proof of completeness for this calculus is the trickiest part in comparison to the soundness and the universality. And the first significant progress on completeness of this calculus was made by William Bacon for stabilized quantum mechanics, which means the angles are multiple of pi by 2. And the next important progress on completeness is made by French team for the Clifford plus T quantum mechanics. So which means the angles are multiple of pi by 4. And based on this Clifford plus T completeness, we have obtained the first universal completeness. That means the angles can be actually real numbers. So this result is incorporated in this Leaks paper. And the key idea is to make isomorphic translation from zeta calculus, which is not graphic calculus, and already universal complete. And also, the technique we use is to introduce new generators, but which can still be represented by green and red spiders. So after that, so use some of our translation from this to ZW. The French team also have a completeness, universal completeness proof. So the difference is that they only use the traditional generators. They don't introduce any new generators. And also based on our P rule, so discovered by me and Bob, Wilma obtained another completeness. And this completeness has the least number of roots. And another way to achieve completeness is to use a homoform for any vector. So the idea is to prove that any state diagram, that means you have no output, no input. Any state diagram can be rewritten into a normal form. So this is also done by the French team in this Leaks paper. So what the completeness looks like? So the simplest one is given in Wilma's paper, and like this: the spider fusion rule, and about identity, the scalar, and the copy rule, and the bialgebra, and the Euler decomposition, and this the color change and the color swapping. So this is very simple one, the form in the. So, but this calculus is not just about completeness. So once we have completeness, we just at the beginning, the right beginning of using this calculus everywhere. So how to use this calculus? So actually, so playing with these diagrams is quite similar to playing with a Go game. In a Go game, if you don't care about any win, then you have no need to learn anything. So you just need to put stones on the board. But if you do want to win, then you need some good strategies. Similarly, if in this calculus, if you don't want to solve any problem, then you can just play with the diagrams by randomly using rewriting loops. But if you do want to solve some problems, then you need good strategy. That means you need to choose good rewriting loops and use them in a nice way. So a typical application of this calculus is to simplify quantum circuits. So for this purpose, we need to translate circuits to these diagrams. This is very easy. That's why this calculus is used for quantum circuits. So you can, as you can see in this diagram, so all the translation is very simple. And now let's take an example for how to use this calculus for T-count reduction. So let's say there is a circuit like this, or there are 4 CCZ gates. This gate can be realized in Clifford plus T set gates. So how do we reduce the T count of this circuit? So the idea is to first translate the CC gate in ZX. So that's there is standard realization. So now you can see that there are 7 T gates in this CCZ gate. So that means all this the whole circuit has 4 CCZ gates, so its T count is 28. So okay, to reduce this T count, so we need to do some rewriting. First, for some small diagrams. So let's look at this diagram. So if we use the fusion loop, so fuse the green node together and then use the other direction fusion, you get this one. And then you move the alpha from here to here, then you got this one. And then you use the other direction of fusion again, you basically extract the alpha. Then you can see this form is a bialgebra form, and then you use the bialgebra loop, you got this one. So basically, this one is this one. So that means you can rewrite this diagram into a simpler diagram. This one we call a phase gadget. And also the C0 can commute with the alpha phase gate. So use the hot floor and the fusion loop. Then you can commute them. So once you commute them, you got a phase gadget. So similar in this way. And also if the phase gadget can also commute with the C0, then you got another phase gadget which has more wires. So in this way, and also phase gadgets, they can fuse into a sum of the angles. And with these rewritings, then we can simplify the CCZ gate. So this is a standard one. Then we use fusion to move the pi/4 phase through the green nodes, and then here we use the technique of C0 commuting with the phase gadget. So in this way, we can do fusion and to commute. So the basic idea is to put all the C0s together. So the C0s, the same C0s, they can cancel out. And then finally, you will get a very symmetric form of the CCZ gate. This means for any wires, you have a single phase gate, have a 2 phase gadget, and three 2 wires phase gadget, and a single 3 wires phase gadget. So very symmetrical one. And then if we put for this original circuit for CCZ gates, if we put all of this symmetric form together, then use the fusion loop of the phase gadget, then you can simplify it in to this circuit. If you count, you can find that the T count is just 8. So it's from 28 to 8. We reduced a lot, right? But actually, we can do better. So remember, we need good strategy for using ZS calculus. So if we can find some new good loops like this identity, it seems this identity is for the phase gadgets. And all these 5 wires identity for the phase gadgets. So I didn't give the angles. And so if you apply these identities, that means these identities can work for the T count reduction. So why? Because if you have half of the phase gadget in this kind of identities, if you already have them in your circuit to reduce, then if you have half of them, if you already exist, then you can. If you apply identities, then your T count will be reduced, right? Now, if we apply the 4 wire identity to the first wires of the circuit, the 4 CCZ circuit, and the 5 wire identity to the whole identity to the whole circuit. After the phase gadget fusion, then we will get a T count of 7. That's the magic. So from 28 to 8 and then to 7. That's how you can use ZS calculus to reduce T count. So based on these techniques, we have the 4 table of how on benchmark circuits on how this how these techniques can be used. And also this one we have more, but this one we have a probabilistic method involved. So that's the that's basically so how you can use the idea, use the strategy of the calculus to simplify quantum circuits. But there is another way to reduce Toount. So if you are interested in this method, and also, or if you are curious about the origin of those spider nest identities, so please attend my talk today in the afternoon. So the use, so you can see that. So I know that some people may wondering that is the theory of the after the completeness result is the theory of this calculus just dead. So there's nothing, there's no more interesting to do. I would say that no. So for example, let's look at the previous universal completeness. So the feature is that they all have some non-algebraic, or they have some trigonometric functions in their roots. So like in this one, this root is in the by the French team. In the completeness, they have some trigonometric function there, and also based on this, we have we can have a question. So can we have a purely algebraic complete axiomatization for this calculus? So without this kind of trigonometry, so, and each root should be as simple as possible. So I would say yes. So if also you are interested, please find my answer in my talk today in session 13. So here I just want to say some further development of the theoretical development of the ZS calculus. So so the first thing, good thing of the if we use the how to say so I mentioned the algebraic style of the ZS calculus. So where I introduce a new generator is the triangle and this green box spider. So basically is so I will show you later. So what does it mean? So basically, it's very similar to the circle style spider. So here I just want to show you some bonus, some good thing, advantage of the this kind of calculus. The first thing is that we can represent any elementary matrices. First, we can represent the low addition elementary transformation. That means the low addition is a matrices. Basically, can be represented by a matrix by, let's say, AG. That means you use the AJ. You use AJ times AJ on the first row and plus it to the J's row, and then you got this matrix. So actually, this operation, this transformation can be represented in ZS calculus in this way. So you have the triangles, and you connect with them with angles, with red node and green nodes, and also you connect with some red nodes. And also, so we can represent the second type of elementary matrices, which is the row switching. So by row switching, we can use the actually the AND gate form of the ZS calculus, use triangles and its inverse, and then you can do the row switching. Here we represent this by the if we want to, for example, this matrix here, if we want to switch the first row and the second row, the last, sorry, the second row from the bottom, and the bottom row. If you want to switch them, then you can just represent by this diagram. And also, there are not just this kind of switching, as you know. So we have also another types of switching. So it's a little bit more complicated, but if you can pay attention to this index, then this kind of switching can be represented by this diagram, and this kind of switching can be represented by this diagram. So basically, that means you can do all of these kinds of things. And the last one is a little bit more complicated switching. Can be represented by this diagram. So all these other low switchings can be derived from this kind of diagrams. So that means you can do the low switching, low addition. And the last one is the low multiplication. The low multiplication, so here you just need to represent the multiplication on the last row. So, and the other one, if you want to multiply on the other row, then you use switch, right? We have already row switch. So basically, you just need to represent this multiplication on the last row. And this diagram form is very easy for the ZX. So you basically it's just the general AND gate connect to each wires. Use the green nodes, and then here is the coefficient you want to multiply with. So it's very simple for the low multiplication from the bottom row, and the others can be used row switching. Okay, so that means we can do all the elementary matrices in the ZX calculus. So basically that means we can use ZX calculus to do Gaussian elimination. And that means we can solve the linear system in ZX in principle. So this reminds us that we can also use ZX calculus to do like quantum machine learning, right? Because one essential thing in quantum machine learning is to solve linear system. So principally we can use ZX for that. So that's a good thing. So another thing is that we can also have a very general normal form for the for arbitrary state. So how do we do that? So basically, since you already have the elementary matrices in ZX, then you just need to start with a unit vector, which is O0, but the last element is 1. And this can be represented by the O red pi diagram, right? O red pi diagram. And then you can see that this vector, you use low addition from the bottom row. You times A0 and pass to the first row, then you got this column. You got this vector, and you do it again, then you got this vector. Again, then you got all of them from A0 to M minus 1, and the last one is just 1. And then you do the row multiplication. You from this vector, then you got a whole vector. This is the object vector, right? So that means if you for any vector A0 to A2 to M minus 1, the AI is a complex number. They can uniquely represent by this form. This is a normal form. So at the bottom, so at the top is all red pi, and then this is a diagram. this diagram, this kind of diagrams is a representation of the row addition. And the last one is the row multiplication. The last one, row multiplication. So actually, I just drew one row addition diagram because all the possible means all the different connections you can have one, and you can have different choice of the connection with the wires with the red nodes. You can the number you can have just one connection, to the connection, and also you can have on this wires or this wires, different all the possible different choices. They are included in this diagram, in this normal form, and they are commute. So then that means you can by this normal form, by this elementary matrices, then you can have the normal form of arbitrary vector. So with this normal form, then of course you can have the proof of completeness, right? So that's another bonus of this kind of this calculus. So, and it's very easy. Once you have this normal form, it's very easy to generalize this normal form to higher dimension, for any higher dimension D. So that means for any qubit, you can represent a vector in a normal form. And so this is so the basic diagram, like represent this vector. And so in qubit, you will have the face is not just a number; it's just is a vector, and but everything is similar. But here you have more wires. You have more wires connection, not just a single wire. But the low multiplication is similar. But here is a special vector like this. So, but generally, that means we can also generalize this normal form to higher dimension D. Then you get QD normal form, and then you can do the completeness. So I would also want to mention that the triangle symbol and is also a generalization of the original triangle symbol, and the green box also they can be represented by green and red spiders. And further is not just to compress numbers for qubits or qubits. We can also generalize the calculus to arbitrary commutative semirings. So to do we need to make a little bit of change of the generators. So now the spider is a green box. I will show the semantics later. And the red spider is just phase free, and we can have a triangle, and we can have the pi, the red pi, is the NOT gate, but because it's in a same ring, then you don't have the Hadamard, right? So actually is the K0 and K1 is basically like this, and then you can see the spike. Now here it's not E to I alpha, it's just A. This parameter is A. Is A. A is the element of the semi. And green spider is like this. Like this. It's just all of them. There actually it means there are just even number of ones. And the triangle is still the same matrix. So in this way, you can represent the diagram. You can generalize the DS from complex numbers to semirings. And even we can go further. So we now have the ZS calculus for qubits and QDs for each D, but actually we want to put them together, put all the QD the ZS calculus put together in how to say, in a single framework. So that means you need a new generator. You need new generator which can connect the different dimensions. So basically, they are unitaries between the different dimension, like two, like for example, is 2, is 3, and 6. So the dimension of 2 and dimension of 6 Hilbert space, and the tens of 2 and 3 dimensions Hilbert space. They have a unitary isomorphism there. So basically, we need this kind of things to connect, ideas to connect them. Now they are not the so now the ZS calculus is not prof anymore. That means it's not generated by one object. It's generated by the by numbers, but the tensor products is not a sum of numbers. It's just a multiplication of numbers. And so if you generalize, if you put them all together in a single framework and you generalize to as far as semi-rings, then you can have the similar, the green spider is still similar in this way. And the green spider is just this index I and index j, they should their sum should be the same modulo d. And the dj and also there is some like the similar to the NOT gate, the phase gate. And also the triangle is actually in matrix form. In matrix form is triangle is the first letter is all 1, and the diagonal is all 1. Yeah, so the other elements are just 0. So that's the generalization of the triangle. And also you have these unitaries between the different dimensions. Okay, so that means you can have this these diagrams, the ZS diagrams in different dimensions. You put them all together, then you can have a single framework. But the idea for completeness is the same, right? Because for each qubit, for now, we have a normal form for them, right? As I just shown, as a normal form for them, and so we would expect that use the same idea, we can have the completeness of the unified, which I call Q-finite ZS calculus, and also. Especially if we restrict the seminar to the field of complex numbers, then that means we can have that means we can fill in the CQM box, each box with the ZS diagram, because now we have all the finite dimensions, right, in a single framework. So in this way, we can really say that the process theory is embodied in ZS calculus. And once we have this, then we can do reconstruction of quantum theory using this Q-finite ZS calculus. That's, I think, is a dream of the calculus. And also, you can expect more applications. So finally, we didn't forget to generalize Q-finite ZS calculus to Q-infinite ZS calculus, such that the standard quantum mechanics, the infinite dimension, can become a standard interpretation of this Q-infinite ZS calculus. So basically, that's the dream of ZS calculus. So I think you are very welcome to join us for this gym, or just using ZS calculus. And you can find us at the zscalculus.com. And that's it. Thank you.
Okay, let's thank Harney. I'm clapping in the channel. I'll clap on my clap. Okay, I thought Ross was typing a question, but he actually just typed woohoo to show some support there. I'll see if anyone wants to type some questions into the Slack. Otherwise, I've got a couple of my own. In the meantime, I can say that you've gotten 7 ZX emojis and a few spider webs and so on. And Ross, in the meantime, has changed his profile picture to the green Spider-Man from your talk. So. Okay, so John Van Vetering asks, the size of your normal form is related to how many zeros are in the matrix. How does this relate to the normal form using the transistor form of the null-C people?
Actually, sorry, I don't know the details of the Nancy people's normal form. So basically, my one is just use the elementary matrices. But definitely, I think there is connections there.
Mm-hmm. Ross asks, regarding the Q-finite version, did you look yet at doing things from the tensor network world in Q-finite ZX? I'm thinking about Mira, that's MERA, and DMRG, etc. So these kinds of tensor network things.
Not yet. Not yet.
Okay. So I was curious, just a remark you made from one of your earlier slides. Could you, well, maybe you'll talk about this later. Could you say something about what kind of probabilistic stuff you're doing in the T-count?
Yeah. Yes. Actually, it's not actually because in a circuit you have the a lot of qubits, and but here we just apply for the 4-wire and the 5-wire identities. So that means you have lots of choices.
Right.
How to choose which wires you would like to apply identities. So we use in this use probability method. So here the probability method is very simple. We don't use there may be maybe other way, but we use very simple way is to uniformly to randomly to choose the wires to apply the identities basically.
Let's see. Ross also asks, regarding the arbitrary semi-ring version, it seems clear that you can define mutually unbiased in an arbitrary semi-ring, but the complementary basis need not exist. Do you know of examples where it does, other than subrings of the complex numbers, and so that the red phases can exist?
So basically the idea use I'll say yes. I think you are right. So now in the sampling case, you don't have it's not like the normal complete the Z and the X spider. They are not in the normal sense of to be complete, to be complementary. But but you can have so that means you cannot have all the red faces, and but you can only have the very typical one like the not gate face. You can have these kind of things. But the good thing is in very general, very bad or bad structure like a semi-ring, you can still have ZX calculus. You can do a lot of matrices calculation. I think that's the good thing.
Okay, if there's no other questions, we can thank Harney again. I'll clap on my own clap there, and yeah, I'd encourage you to go ahead and join your own Slack channel and keep chatting with people as they have questions there.
Okay,
okay, so with that, Harney, you can disconnect from the call if you like. We're switching over to John Selby.
I can close it.
Yeah. Are you there?
Yeah, I'm here. Can you hear me?
Yep.
Great. So I should figure out how to do a screen share thing, shouldn't I?
Yeah, I think you should.
No, that's not it. How do I do this?
So there's a button that says share content along that list. It looks like a little sharing symbol. You see this kind of row of buttons?
Yeah, I see it.
Yeah, and then you click that, you click share content, and then click screen, and then
yeah, okay.
And then click share. You may need to.
Quite obvious, really, isn't it?
There we go. Okay, so I'll just hand it over to you then.
Okay, great, thanks. So I would like to announce that QPL next year is going to be held in Gdansk and Sopot. So this is a picture of Gdansk. It's a very pretty city. And where are they? Well, they're in Europe, which is this place here. In particular, they're in Poland, which is this country here. And they're actually on the coast in the north on the Baltic Sea. Interestingly, they're a very short drive away from Hell and a seal sanctuary, so we can have a trip there if we want. Sopot is a small beach town. It's probably where the conference venue will be, because it's right next to lots of cafes and pubs and restaurants and the beach if people want to be mad and go for a swim in the Baltic. And then Gdansk is an older town, which is very close by. It's only about 30 minutes away on a train. They're sort of merged into one, or you can get an Uber for basically very cheap. And that's where I expect the conference dinner will be. There's a pirate ship, and then there's lots more cafes and bars and pubs. So it's a great city. What's going on? Yeah. So this will be supported by the University of Gdansk and the International Center for the Theory of Quantum Technologies. There's some information about it here and funding people and all of that business. I'll put these slides available somewhere if people want to look at this in more detail. The most important thing is the potential dates for the conference. I am going to suggest one of these 2 weeks, either the 7th to the 11th of June or the 14th to the 18th of June. And please, if you know of any conflict with any other conferences or anything else, please get in contact with me so I can not end up with any clashes. So why Gdansk and Sopot? Well, I think the most important reason is that it's very cheap here. We can get a beer for about £1. Accommodation should be cheap, and food and all that's cheap. So we'll get a lot for our money. And it's very convenient for people to get to as well. There's ferries, or there's trains, or there's cheap Wizz Air flights. Very well connected. But more importantly than all of that is, number one, the Polish beer is very good, and there's lots of it. Number two is the Polish food. It's also very good. In particular, pierogies are amazing. And finally, how do we know that we're not all going to still be trapped at home and not be able to make it to Gdansk for QPL 2021? It's very simple. That Polish vodka kills coronavirus. So that's it. Thank you for listening, and hope to see you all here next year.
Looking forward to it. Thanks, John.
Thanks. I don't know how to get out of screen sharing. There we go. If there's any questions or anything, feel free to message me on Slack. And yeah, please let me know if there's any conflicts with those dates I suggested.